All right, everyone, we're on page 25, 25.
Yeah.
No, your test will be back at the end of the week. I was away all weekend, and I've been getting caught up. Page 25, 25. So a shift. A shift is an equilibrium's response to a stress. Now, do you remember how much time a stress took? No time at all. It was instantaneous. However, shifts take place over time. Okay, so you're not going to see a spike when you're shifting. You're going to see a gradual transition. Okay, so we have shifts. Will shift until the reverse and forward rates are equal again, and the shift will always take place gradually over time. The shift is fast at first, and then it slows down as time goes on. Hi.
And some of my stuff in the library.
Okay, yes. So the shift is quickly at first. So when something is fast on a graph, that means that the slope is steep or shallow. You're late. If you have a rate of change which is fast, will you have a steep slope or will you have a shallow slope? Steep. Okay, so we have a fast and then it slows down as time goes on. That means the slope is going to get more. Charlene, you're late. Slope gets shallower. And on a concentration graph, this appears as a curve with an initial steep slope and becomes more shallow over time. So if this is a concentration graph, let me just make sure I correlate this correctly with the answer key. So we have our concentration. What goes on the x-axis? What goes on the y-axis? Or sorry, the x-axis? Time. Excellent. So you can put time there. Okay. 2A, where are we? Okay. Yes. Okay. Yeah. So here we have our forward rate. Here we have our reverse rate. And initially, oh, I'm sorry. Am I doing rate or am I doing? I'm doing concentration. Stress, shift. Okay, I'm doing concentration, so I'm not doing forward and reverse. So this would be, sorry. making a mess here. We would have maybe our NO2 and our N2O4. All right, and when we increase the concentration, oh, that's why I'm looking at the wrong page. Oh, silly me, silly me, silly me. And remember, our reaction is N2O4 in equilibrium with 2NO2. Yes, and if we increase the concentration of N2O4, what is that? No, we increase the concentration of N2O4. Is that a stress or a shift? That's a stress because we do it. And how much time does a stress take? No time at all. So there's our stress. N2O4 goes up. All right. And then we're going to show the shift. Now, if I have increased the concentration of N2O4, which rate is going to have gotten faster? The forward or the reverse? If I've increased concentration of N2O4, which rate got faster? The forward rate got faster and the reverse rate stayed the same for right now. So are we using up N2O4 or are we making N2O4 net? And when I say net, I mean, are we using it up faster than we are making it, or are we making it faster than we are using it? We're using it up faster than we are making it. So the concentration of N2O4 is now going to decrease, okay? And when we draw our curve, remember it starts steep and it becomes more shallow. It's actually going to finish above where it started. Okay, so it starts steep, it becomes more shallow, and eventually it will flatten out. Okay? So this is steep, shallow, flat. It should always be steep, shallow, flat when you have a curve. Okay, concentration diagram. Now, what is going to be happening to our concentration of NO2 as time goes on? Remember, the forward rate is happening faster than the reverse rate. So it's going to increase. And by what ratio will it increase? Yeah, we remember for every one N2O4 that breaks down, we make 2 NO2. So I'm going to end up making twice as much. All right, so that's going to go up, and it's going to go up steep. And then it's going to go shallow and then flat. So steep, shallow, flat. Steep, shallow, flat, steep, shallow, flat. They do follow the stoichiometry of the equation in a 1:2 ratio. Okay, so that is what a concentration diagram looks like. All right. Let's carry on here. So here is a sample problem. You are going to do the following. You are going to label the old equilibrium. You are going to label the stress. You are going to label the shift. And you are going to label the new equilibrium. You can just like circle it and put an arrow at it or whatever, or put a bracket around it or something like that. Okay? So give that a go. That color. Great. I'm making a fuss about the lateness today because everybody was late. Not everybody, but there were a lot of late people. Ah, okay, no worries. Thank you. It's okay. Hopefully you've all managed to label the old equilibrium where the two rates are equal. Where is our stress? It's that spike there. Okay, so that's our stress. And where is our shift? It's the curve, okay? So the curve is the shift. Okay, so this part here, this is the shift. And then finally we have the two rates are equal again. Our new equilibrium. Yes. We will, well, the shift is just this area in here. This area in here is the shift. It would be the bottom part as well. Yeah. And then we have our new equilibrium. I'm never going to have you label a diagram like this, but I could say something like, at what time is the new equilibrium established? And if you had times on the bottom axis, you would have to be able to read it. Okay? All right. At the moment of the stress, what happens to the forward and reverse rates? What happens to the forward rate at the moment of the stress? Tell your partner. The forward rate does what? Forward rate increases. What happens to our reverse rate? Nothing. It stays the same. Are the beginnings of the slopes, are the slopes at the beginning of the shift steep or shallow? Tell your partner. Take a look at the beginning of the shift. Is that steep or shallow? It is steep. Okay, that beginning of the shift. If you were skiing or something, or going down a hill, you'd be like, or going down a slide, you'd be like, ah! Right? A water slide, you'd be freaked out. You'd be like, oh my gosh, this is so scary. Okay, so at the beginning, it is steep. And because it is steep, that means that at the beginning of the shift, the rates are changing. A steep slope means fast. Okay, they're changing quickly. Steep slope means fast rate of change. Are the slopes at the end of the shift steep or shallow? They're shallow. That means at the end of the shift, the rates are changing slowly. Okay, so you can try the next one. This one is a concentration diagram. So we just did a rate diagram. Now we're looking at a concentration diagram. So did that go okay? All right, you can label it whichever way you want. Like I said, I'm not going to have you label a diagram like this because it's awkward and, you know, where am I putting things? How am I showing it? But it's helpful when you're first looking at it to start to recognize, this vertical line is a stress. This curve is a shift. And when it is flat, we are at equilibrium, okay? And what was the nature of the stress? Like, what did we change in this particular diagram? We changed the concentration of NO. So the stress was a change in the concentration of NO. Specifically, we increased the concentration of NO. Okay? All right. Now, a lot of this is just repetitive. Are the slopes at the beginning of the shift steep or shallow? Steep. This means that at the beginning of the shift, the concentrations are changing quickly. Are the slopes at the end of the shift steep or shallow? They are shallow. And that means at the end of the shift, the concentrations are changing slowly. Concentration is an example of what kind of property? Macroscopic. What does macroscopic mean? Observable. And what can we say about concentration at equilibrium? Is constant. Is good? Okay. So these are just, this is just, you know, if you didn't manage to do a beautiful job, because sometimes I don't do a beautiful job when I'm actually labeling it. I let the computer help me out, showing the stress, the shift, and the new equilibrium, the stress, the shift, and the new equilibrium. Okay, so when the system is at equilibrium, the forward and reverse rate are the same. The concentrations, are they the same? No, they are, or different. Okay, the concentrations are different, but not, they are constant, but they are not the same. That's what I'm trying to say. The concentrations are constant, but not the same. A stress is signified by a vertical spike. A shift is shown as a curve. Now, because the rate of change is fastest at first, the change from stress to shift is sharp. Do you see how that looks sharp? Pointy, you could poke yourself on that corner. Yes? This is what I often see from students because they're not being careful in their drawings. Is this sharp? Not really. Yeah? We don't want to see any S curves. No S curves. Okay? No S curves. What would it mean if I had this S curve? It would mean that the concentration changes slowly, yes, because I got a shallow slope, and then the concentration changes quickly, and then again, finally, the concentration changes slowly again, and that's not what happens. It's fast rate of change and then slower rate of change. It's not slow, fast, slow. Okay? So you can think of it in terms of the rate of change. It's always fast rate of change, then it gradually becomes slower. Or you can think about it as you need a sharp transition, or you can think about it as not having any S curves. I don't care which one that your brain chooses, but just don't draw me things that look like that because I will be very sad. And you will be very sad because you will not get full credit for it. Okay? All right. Same thing for rate diagrams. Okay, rate diagrams, same thing applies, no S curves. It should be sharp. You should have a fast rate of change and then a slower rate of change. Okay? So this is when you're drawing diagrams, make sure you don't do this. No. Now, please feel free, if you need to borrow a ruler when you're doing your quiz or your test, to borrow a ruler, because if you cannot draw an approximately straight line, then that's too bad, right? I mean, I don't know why my son has trouble drawing straight lines. He's 21 years old. I don't know what is wrong with him. Like, I'm like, why can you not just draw a straight line? But when he draws a line, it's like this. And I'm like, what? What are you doing? Like, are you, like, I don't even know. I just don't know. And he's too old for me to fix it. So I'm like, I guess that's where we're at. So, but he's brilliant. So you may also be brilliant and not able to draw a straight line. Okay? So it's okay if you can't. If you can't, just get yourself a ruler. Because if you draw it like this, that means the concentration is increasing. Yes? At the end, concentration is increasing. Oh, concentration is decreasing. Now, if you can draw a fairly flat line, that's okay. It doesn't need to be perfect. Like this would be okay, this would be okay. You know what I mean? Like it doesn't have to be perfect, but I don't want it to look like that. You know, I don't want your horizontal line to be on an angle or curving. Okay? At equilibrium, the macroscopic properties are constant, and therefore we won't want it to curve. What are some other macroscopic properties? I would like you to list them together with your partner or on your own, whichever you prefer. See if you can list some other macroscopic properties. Hmm? I heard temperature, yes. Color, yes. Density. pH. pH only if there's an acid or base present, because otherwise you won't have a pH if it's not acidic or basic. Pressure, yes. And that's if there's gases present. If there's no gases, obviously pressure won't come into play. I'm sure there's some other ones, but those are sort of the main ones, okay? Okay. Is that it? That's it for this one. Okay, yay. All right, 2.2b, moving right along. Wah! What are we looking at in 2.2b? Oh, we're looking at what happens when the stress is a change in concentration. We're going to do a whole bunch of graphing here. Stresses make the rates unequal. Are we on the right page now? We should be on page 29. The shifts make the rates equal once again. So let us take a look at this system. It is at equilibrium. What can you say about the rates of the forward and reverse reaction? They are the same. The forward rate is equal to the reverse rate. Okay, so what that's going to look like on our graph is that we are going to have our forward rate and our reverse rate. Here's our forward rate. Here's our reverse rate. And we are at equilibrium. If we increase the concentration of H2, now remember, our reaction looks like this. H2 plus I2 gives 2HI. Okay, that's our equation. If we increase the concentration of H2, what happens to the forward rate and why? You guys are going to say increase, decrease, or stay the same. If we increase the concentration of H2, remember this is our reaction, H2 is a reactant, will the forward rate increase, decrease, or stay the same? Forward rate will increase because we have more H2 particles in the same space. Therefore, more collisions. Okay, so what should it look like for my blue line? What should my blue line do? It should go straight up. Okay, that's great. What happens to my reverse rate when I increase the concentration of H2? Does reverse rate increase, decrease, or stay the same? Stays the same. Why? We have not changed the concentration of the reactant for the reverse reaction. The concentration of HI has stayed the same. It has not changed. I'll put yet because it will change, but it has not changed yet. Therefore, same number of collisions. Which reaction is favored? This is a new kind of word that we're going to use. Favored means to go faster. So which reaction is going faster? The forward rate. So the forward reaction goes faster. Therefore, we say the forward reaction is favored. Okay, so far what we've looked at is we've looked at what's happening in when we're at equilibrium, when we have a stress, and now we're going to look at what happens when we have the shift. So as a result of the forward reaction, being faster than the reverse reaction, the system is now shifting because we shift when the two rates are unequal. As it shifts, what happens to the concentrations? And remember, this is our equation, H2 plus I2. And remember, our forward rate is faster than our, actually, I should have written this up above because I'd have more room. Let's try that again. We have H2 plus I2. Forward rate is faster than the reverse rate, 2HI. Take a look at that and decide what is going to happen to the concentration of H2. I would like you to discuss that with your neighbors. Okay, H2. Which process is faster? Using up H2 or making H2? Using up H2, okay, because the forward reaction uses it up. So if we're using it up faster than we're making it, the H2 concentration is going to decrease. How about I2? What will happen to the concentration of I2? Same thing, because it's on the same side of the equation. Now, HI, are we using it up faster or are we making it faster? We are making it faster, therefore its concentration is going to increase. Which means, which direction are we shifting? We are shifting to the right. Now, as the H2 goes down and the I2 goes down, what happens to the forward rate and why? Tell your partner. Does the forward rate increase, decrease, or stay the same? Increase, decrease, or stay the same? 5, 4, 3, 2, vote. It decreases because we have fewer particles and therefore we have fewer collisions. So the forward rate decreases because we have fewer H2 and I2 particles, therefore fewer collisions. So the forward rate is going to start to decrease. Is it going to start to decrease fast, or is it going to start to decrease slowly? It will start to decrease quickly, because remember, the rate of change is always quickest at first. And then what happens to the concentration eventually? Or eventually it will become constant. So what has to happen to that line now? The curve has to become more shallow, and then eventually it will become flat, okay? And it has to end up above the original line. So I'm just going to draw that line there, and I'm just going to make sure that I end up with my concentration. Oh, no, I'm a dummy. This is not concentration. This is rate. Oh, Lordy. I'm so sorry. Okay. The rate changes quickly at first. Rate. Rate changes quickly at first. All right. What happens to our reverse rate as the system is shifting to the right? As the system shifts right, the concentration of HI increases. Therefore, there are more collisions. Therefore, the reverse rate increases. Okay, so the reverse rate is going to increase. Will it increase at a fast rate or a slow rate at first? Fast rate. So it's going to be steep or shallow? Steep. Oh, look at that. Yes? And eventually, what will happen to those two rates? They will become constant and the same. And if you have trouble, like I personally find I can go like this, but I can't go like this. Like this is a hard line for me, but if I move my body or I move my page, I can draw much better. Okay? So if you need to move your page or move your body or whatever, some of you are natural artists, you will not need to do this. Some of you may need some help, like me. Huh? Okay? And technically, it would be better if I could get those two closer together, but that would be fine. I'd be like, okay, you're meaning that they are the same, okay? Technically, they're the same. Very good. So that would be a rate diagram for what would happen if the H2 concentration was increased. Now, eventually, after the shift, we would have the H2 plus the I2 in equilibrium with 2HI. What would the sizes of the arrow be like compared with those ones? Once the shift is finished, we are at equilibrium. The sizes of the arrows would be the same, and they would be somewhere in between those two sizes, yes? So we would have like this. Now, technically, you're not going to be drawing these arrows at different sizes. This is to help you visualize it. Normally, anytime you write an arrow, you're just going to be like blah, 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 right? And they'll always be approximately the same size. But this is just to help you visualize the rates in comparison to one another, okay? We are going to draw a concentration diagram for exactly the same process. So once again, we have our H2 plus I2 gives 2HI. And just take note that because we are mainly concerned with the stress and the shift, the initial concentrations are often just set arbitrarily. We have set them at random. So do I care whether I put H2 at the top or I2 at the bottom or wherever? It doesn't really matter. I think this diagram goes a little bit better if I put H2 here and I2 here and HI here, but it really doesn't matter. You could pick where you set them, okay? What would we label our y-axis? The y-axis? Y-axis would be concentration in molar. Okay. And what was our stress again? H2 plus I2 to HI. It was an increase in the concentration of H2. So what would that look like on the graph? So at this time, we increase the concentration of H2. So we should see, guess what? An increase in the concentration of H2. Shocking. Whoa, look at that. Oh, okay. So there we go. Now this is what I was trying to do last time, but I was not drawing a concentration diagram. Now, when it starts to shift, which direction does it shift? Does it shift to the left or does it shift to the right? It shifts to the right. Oh, look. It shifted away from an increase. That's going to become important because you can make a quick prediction by saying, if I increase concentration of H2, it shifts away from that increase. And that allows you to tell the direction of the shift really quickly. Okay, but don't worry about that. I'm just giving you a flavor of that. We'll go through that later. Okay, so H2 goes up. If we are shifting to the right, what will now happen to the H2 concentration? It will decrease. And what will it look like? Will it look like this? No, what have I done wrong? I've made an S curve. What should happen at the very beginning? It should be steep. Where should I end? I should always end above or below if I happen to decrease it. I should never go past or to the initial concentration. Okay, so in this case, that means we're going to have to end up above it. So I'm going to aim for ending here. Okay, and then I'm going to fill in my curve to make that happen. Now, if we are shifting to the right, what will happen to the concentration of I2? It will also decrease. By how much compared to the H2? By the same, because these guys are present in a 1:1 ratio because they each have a coefficient of 1. So what I'm going to do is I'm actually going to do a little bit of labeling, and I'm going to say this distance here, I'm going to call that distance X. Okay? Because if I'm really good at drawing, I can make my distance X look approximately the same. Yes? But if I'm not good at drawing, which some of us are not, and let's say I drew my thing like this, and I got my H, and then this one goes down like that, and then my other one, I'm like, my I2 goes down like that, right? Okay, number one, I don't want the scoopy curve, but number two, I want these two to be the same distance, and if I haven't quite managed it, if I label this one X and I label this one X, even if my drawing is crap, I know that you meant them to be the same size. Does that make sense? So if you're really good at drawing, if you're, you know, like you've got a good eye for things and it's very obvious that they're the same, you don't have to label it. But if you're not good at drawing, I would recommend labeling these as X and X. Now we are shifting to the right. What will happen to the concentration of HI? It will increase by how much? Twice as much, 2x, because we make 2 HIs for every 1 H we use up. We make 2 HIs for every 1 I2 we use up. Okay, so it has to go up by 2x, which to me would probably be about here. And if it's not, that's okay. So what I'm going to do here is I'm going to say, okay, this is going to go up by 2x. And so the system has shifted to the right. Do you guys need a little 5-minute break? Okay, so be back here at 1:25. Because that clock's fast. It's really only 1:21. I'm going to reset my clock, but it should be. I'm like, no. That's straight. That was straight up and down. I'm not ready to. I'm not. I gotta say yes. I'm dying. I'm rich. I know.
So late. I have it.
Now she's explaining observation.
Hi.
Bars on the for the concentration.
Mm-hmm.
This means this.
This is just the initial concentration, right?
Yeah. So like.
It's not there other.
Should I draw this 2xr here, like at the same time.
Oh, I'm just showing the distance. It doesn't matter where I show the distance.
Oh.
Yeah, it ends up here, but whoops.
So it doesn't really matter.
It doesn't matter where you draw it. No,
Okay.
no.
Why are you here?
Okay, back to work. So we're on page 31. When we increase the H2, the system shifted to the right. Okay, we are starting. Okay. Are there any other concentrations any other concentration changes we could make to get the system to shift to the right? Yes, we could increase, what could we do? We could increase the concentration of I2. So remember, we've got concentration over here and we have time down here. And how do we set up where things go? We just assign them arbitrarily, in other words, randomly. So this time, you know what I'm going to do? I'm going to say, let's make this one HI. Okay, let's make this one I2. And let's make this one H2. Just whatever, just to say for example. Now, at this time right here, we are going to increase the concentration of I2. See if you could draw what would happen in that case. Does your graph look something like that? What you should be looking for is to make sure there are no S-curves. You should make sure the change in HI is 2 times because we have coefficient of 2. HI should be twice as much as the change in I2 and H2. You should make sure that the I2 ends up above where it started. And because we increase the concentration of I2, we are going to be shifting to the right. We always shift away from an increase in concentration. If you're not finished drawing that, you can finish drawing it. If you are finished drawing it, you can think, is there any other concentration diagram, or sorry, any other concentration change that would shift the reaction to the right? Have a chat about that. If you're done drawing, you should be chatting. Now remind me, why does an increase in concentration of I2 cause a shift to the right? Because the rate of the forward reaction increases. Why does an increase in concentration of H2 cause the equilibrium to shift to the right? Because the forward rate increases. We only have one thing left. What could we change? We could change the concentration of HI. To get this thing to shift to the right, would we need to increase concentration of HI or decrease concentration of HI? We would need to decrease concentration of HI. And that will cause a shift to the right. Guess what? Shift is always towards a decrease in concentration, towards a decrease. Away from an increase in concentration, towards a decrease in concentration. If we decrease the concentration of HI, what happens to our forward rate? No change. So it stays the same. Forward rate is unchanged. What happens to our reverse rate? Because we have less HI, we have fewer collisions, and therefore the rate will be slower. And if the reverse rate is slower than the forward rate, that means that the forward rate is faster than the reverse rate, which means you are shifting to the right. You are making product faster than you are using it up. Does that make sense? So there's two ways to make the forward reaction faster than the reverse reaction. You can either speed up the forward reaction or you can slow down the reverse reaction. Okay, so here we go. Let us draw a concentration diagram for what happens in this case. So we have HI. Don't worry, we'll come back to that later if you didn't manage to get it all down. We have I2 and we have H2. Concentration, time. And at the time rate here, we're going to decrease the concentration of HI. So HI will go down. Then it will go down more. I'm shifting to the right. Remember, I have a decrease in the concentration here. So that means my forward rate is faster than my reverse rate, which means I'm going to be making more HI. Okay, so the concentration of HI is going to go up again. And it's going to go up quickly at first, and then it's going to slow down, and then it's going to level out before it gets to its original concentration. So our forward rate is faster than our reverse rate because we slowed the reverse rate down. So we are making HI faster than we are using it up. And that's why the concentration of HI increases. What will happen to the concentration of I2 and H2? If we are making more product, we must be using up reactant. Yes? So if we're making HI, we must be using up H2 and using up I2. So those concentrations are going to go down. All right? By how much should they go down? Half as much. So I'm still going to call this 2x. You could call it x and then have half x, but I like whole numbers. Whole numbers are easier for me. So this is going to go down by x. And this one's going to go down by x. And I feel like maybe I should have used a ruler here, but I'm just going to straighten it out like that. There we go. Okay, and your homework is going to be to read Habden Habden. Because we didn't finish this today, but we're going to be talking about Le Chatelier's principle. So pages 50 to 54. And you're going to do exercises 17 through 20. On page 54. Give them a try anyway. And don't worry, if you're confused by it, if you're like, oh my gosh, that was too much all at once, we're going to be doing more in-depth tomorrow and the next day, okay? All right, lovelies, have a good afternoon. I will see you tomorrow.